Hey everyone, welcome back to the Wawa Lighting Podcast.
Yeah.
For a special deep dive into the fascinating world of electric light sources.
We're going on a journey through time,
You got it.
exploring how those little points of light that we often take for granted have actually revolutionized the way we live, work, and experience the world around us.
Yeah, from those old school incandescent bulbs that many of us grew up with, to the mind-blowing LED technology that's lighting up our world today.
And even beyond,
Oh yeah.
to those cutting-edge innovations that are shaping the future of illumination.
So we've got a stack of sources here.
Articles, research papers,
Yeah.
even some quirky anecdotes.
Correct.
And our mission...
Is to sift through it all.
Exactly.
Extract those golden nuggets of knowledge.
And by the end of this deep dive, you'll be able to walk into any room and confidently decode the lighting.
You'll know what's happening behind those glowing fixtures.
Yeah, it's less about decoding and more about appreciating the ingenuity behind each technology. We're going to uncover those aha moments that make you see light in a whole new way.
All right.
So where do we begin this illuminating adventure?
Well, we got to start at the beginning, right?
Yeah, let's kick things off with the OG.
The OG.
The one that paved the way for everything that followed.
The incandescent lamp.
The incandescent lamp.
Ah, yes.
The classic light bulb.
The classic light bulb. Simple, familiar.
A nostalgic reminder of childhood for many of us.
Yeah, but I bet there's more to this seemingly basic invention than meets the eye.
Absolutely right.
Right.
The incandescent lamp is a testament to the power of simple yet elegant engineering at its heart.
It's just a thin tungsten filament.
A thin tungsten filament.
That glows when an electric current passes through it.
Right.
It's remarkable how such a basic principle can produce something as transformative as electric light.
It really is.
I remember reading that the choice of tungsten was actually a major breakthrough.
It was.
Because it has the highest melting point of any metal, which is crucial for withstanding those scorching temperatures inside the bulb.
That's exactly right. Early incandescent lamps used filaments made of carbon or other materials,
Right.
but they weren't nearly as durable or efficient.
Right.
Tungsten's ability to withstand intense heat without melting quickly allowed for brighter and longer-lasting bulbs.
And yet, for all its brilliance,
The incandescent lamp has a rather glaring flaw.
its inefficiency.
Its inefficiency.
I recall learning that most of the energy it consumes is actually converted into heat, not light.
It's true, incandescent lamps are notorious energy hogs.
Yeah.
Which is why they've been largely phased out in favor of more efficient options. But there's a fascinating anecdote about this inefficiency in our sources.
Oh, really?
It seems that in some colder regions, like the Northwest Territories of Canada, people actually appreciated that extra heat from incandescent bulbs during the long winter months.
Oh, that's interesting.
Talk about turning a drawback into a benefit.
Yeah, that's a classic example of how context can change our perspective on technology.
It really is.
What's considered a flaw in one scenario might be a welcome feature in another. But even with those occasional perks, the incandescent lamp's days were numbered, as concerns about energy efficiency grew.
They were.
So what came next in this evolutionary saga of light?
Well, enter the halogen lamp.
Oh.
An ingenious refinement of the incandescent concept that aimed to address its shortcomings.
Okay, so halogen lamps.
They look a lot like traditional incandescent bulbs, but I know they're supposed to be brighter and longer lasting.
What's the secret behind their improved performance?
It all comes down to a clever addition.
Okay.
A touch of halogen gas inside the bulb.
Got it.
Now, this isn't just any gas. It sets off a chain reaction known as the halogen cycle, which is fascinating. Essentially, as the tungsten filament heats up and evaporates the halogen gas, helps redeposit the tungsten back onto the filament.
So it prevents it from...
Preventing it from thinning out too quickly.
Interesting.
It's like a miniature recycling system within the bulb itself.
I like that.
It really is, and the implications of this halogen cycle are significant. By preventing the filament from degrading, as rapidly halogen lamps can operate at higher temperatures, producing a brighter and whiter light than standard incandescents.
Which is why we see them in car headlights and spotlights, where you need that intense focused beam.
Precisely, and the added benefit is that halogen lamps generally last longer than their incandescent counterparts.
Which is a win-win.
Which is a win for both convenience and sustainability.
Now, I've also heard of something called cool beam halogen lamps.
Yes.
Is that just a marketing gimmick?
Cool beam halogens are anything but a gimmick.
Okay.
They utilize a special dichroic coating on the reflector,
Okay.
which plays a crucial role in heat management. This coating allows visible light to pass through while reflecting infrared radiation, the primary culprit behind that unwanted heat.
So they redirect the heat away from the illuminated object.
Exactly.
That's brilliant.
It's brilliant for applications where heat is a concern, like illuminating artwork or delicate fabrics.
Yeah.
Cool beam halogens allow you to achieve that focused illumination without the risk of overheating or damaging sensitive objects. It's a testament to how subtle tweaks in design can have a significant impact on a lamp's performance and applications.
Yeah, it's all about understanding those nuances, isn't it? But while halogen lamps were a definite improvement over traditional incandescents, they were still relying on that same basic principle of heating a filament to produce light.
Right.
Was there a point where lighting technology took a more radical departure from this approach?
Absolutely. The next major leap forward in lighting efficiency came with the development of fluorescent lamps.
Okay.
These are those long, tubular lights you often see in offices, schools, and commercial spaces.
Right.
They operate on a completely different principle than incandescents and halogens, and their impact on energy consumption was significant.
Yeah, fluorescent lamps, they're certainly ubiquitous.
They are.
But I have to admit, I've always found them a bit mysterious.
Yeah.
How do they manage to produce light without a glowing filament?
It's a fascinating process. Instead of heating a filament, fluorescent lamps rely on exciting mercury vapor inside a sealed tube.
Okay.
Now, I know the word mercury might raise some eyebrows, and rightfully so. Mercury is a hazardous substance, and it's crucial to dispose of fluorescent lamps properly to prevent environmental contamination.
Yeah, safety and environmental responsibility should always be top of mind when dealing with any technology, especially one that involves potentially harmful substances.
Absolutely.
But let's get back to how these lamps actually work.
Right. So inside that sealed tube, an electric current excites the mercury vapor, causing it to emit ultraviolet UV light. Now, UV light is invisible to the human eye, so here's where the magic happens.
Okay.
The inside of the tube is coated with a phosphor powder, and when the UV light hits this coating, it converts it into visible light.
So it's like a chain reaction.
That is.
Electricity excites mercury vapor producing UV light, which then interacts with the phosphor coating to create the light we see that's a far cry from a simple glowing filament.
It is, and here's where it gets even more interesting. The type of phosphor used determines the color of the light emitted.
Okay.
By carefully selecting different phosphors, manufacturers can create a wide range of colors, from warm white to cool white to daylight, all from the same basic principle of fluorescence.
That explains why fluorescent lights come in so many different color temperatures.
Right.
And don't forget those ballasts.
The ballast.
They're an essential part of any fluorescent lighting
Yep,
setup.
they absolutely are. The ballast acts like a regulator controlling the flow of electricity to the fluorescent tube. Without a ballast, the tube would simply burn out.
Oh.
It's like having a surge protector built right into the lighting system.
Those older fluorescent lights with magnetic ballasts used to flicker and buzz quite a bit, especially when they were first turned on. Not the most pleasant experience.
That's right. Magnetic ballasts were the standard for many years, but they were prone to flickering and noise, especially as they aged. Luckily, technology marched on, and we now have electronic ballasts, which are much more efficient, quieter, and provide near-instant start with minimal flickering.
That's a definite improvement. I also recall reading that fluorescent lamps can be sensitive to temperature extremes. They don't perform as well in very cold or very hot environments.
Yes, that's another factor to consider. Fluorescents are most efficient within a specific temperature range. In fact, one of our sources mentions an anecdote about compact fluorescent lamps, or CFLs, failing prematurely when used in enclosed light fixtures due to heat buildup.
CFLs. Those are those spiral-shaped bulbs that were marketed as the energy-saving replacements for incandescent bulbs, right?
Exactly. CFLs are essentially miniaturized fluorescent lamps designed to fit into standard light sockets. They offered a more compact and energy-efficient alternative to traditional incandescent bulbs, but they weren't without their quirks.
Like what?
Well, they were sensitive to frequent switching, which could shorten their lifespan, and some people found that they didn't dim as smoothly as incandescent bulbs.
Right.
However, one interesting tidbit from our sources is about California's Title 24 energy regulations.
Okay.
To prevent people from swapping out CFLs with less efficient incandescent bulbs, they mandated the use of light fixtures with pin bases instead of the standard screw bases.
Yeah.
It's like a built-in nudge towards energy efficiency.
That's a clever way to encourage the adoption of energy-saving technology.
Yeah.
So CFLs were a step forward in terms of energy efficiency. But were there any other major players in the lighting world before we get to the LEDs that we know and love today?
There were a couple of other notable lamp technologies, but they weren't quite as widespread as incandescence or fluorescence for general lighting purposes.
Okay.
One of them is the high-intensity discharge, or HID lamp.
High-intensity discharge. That sounds powerful.
Think big, bright, and efficient.
Okay.
HIDs are commonly used in large spaces that require a lot of light. Sports stadiums, warehouses, even street lighting, they pack a punch when it comes to light output. But their use in indoor spaces can be tricky due to the color of the light they produce.
What do you mean?
Well, color rendering is a crucial aspect of lighting design, and not all HID lamps excel in this area. Color rendering refers to how accurately a light source reveals the colors of objects compared to natural daylight.
So a light source with poor color rendering might make colors appear washed out or distorted.
Exactly. And while some HID lamps have excellent color rendering properties, others can leave things looking a bit drab or unnatural, which isn't ideal for spaces where color accuracy is important, such as retail stores or art galleries.
I see. So which HIDs are better suited for indoor use?
The ones that offer good color rendering are metal halide, MH, and ceramic metal halide, CMH lamps. They produce a more natural and vibrant light that accurately reveals the colors of objects, making them suitable for a wider range of applications.
Gotcha. Are there any other lesser-known lamp types that we should be aware of?
There's one more worth mentioning, even though it's not as commonly used indoors. The sodium vapor lamp, it's a champion when it comes to efficiency. But its color rendering is, well, let's just say it leaves a lot to be desired.
Sodium vapor lamps. Those are the ones that give off that distinctive orange glow, right like the streetlights in many cities.
You nailed it. High-pressure sodium HPS lamps are responsible for that iconic orange hue, and their poor color rendering is why things look different under streetlights at night. Colors appear distorted and washed out.
Right.
There's also a low-pressure sodium LPS lamp, which emits an even more limited, almost purely yellow light.
So sodium vapor lamps are all about maximizing efficiency, even if it means sacrificing a bit of color accuracy.
Precisely. They have their specific applications like street lighting and security lighting, where high visibility is paramount but color accuracy is less critical.
It's fascinating how each lighting technology has its own strengths and weaknesses, and finding the right fit for a particular application is all about understanding those trade-offs.
Yeah, you've got it. And that brings us to the real stars of the show these days, LEDs, or light-emitting diodes.
LEDs.
They've taken the lighting world by storm, and for good reason.
LEDs.
Yeah.
They're everywhere. Our phones, our TVs, our homes, our cars. It seems like they've become the go-to lighting solution for just about everything but what makes them so special.
Where do we even begin? LEDs are like the overachievers of the lighting world.
Okay.
Efficient, long-lasting, incredibly versatile, and constantly evolving.
All right, before we get too carried away with their glowing accolades,
Okay.
let's break it down for our listeners. How do these tiny marvels actually work?
LEDs are based on semiconductor technology, which is a fancy way of saying they use special materials that emit light when an electric current passes through them. Think of it like a controlled flow of electrons that excites the semiconductor material, causing it to release photons, which are the building blocks of light.
So it's a completely different principle than heating a filament to produce light like in incandescent or halogen lamps.
Exactly, and this fundamental difference is what gives LEDs their remarkable edge.
Okay.
They're incredibly efficient,
Yes.
converting a much higher percentage of electricity into light compared to those older technologies.
Yeah, that's a huge win for both our wallets and the environment. Less energy wasted means lower electricity bills and a reduced carbon footprint.
Exactly.
What else makes LEDs so special?
Their lifespan is phenomenal. We're talking tens of thousands of hours, sometimes even exceeding 50,000 hours compared to the mere hundreds or thousands of hours for traditional bulbs.
That's practically a lifetime of lighting.
This means fewer replacements, less waste, and long-term cost savings.
I'm sold on LEDs for those two reasons alone, but I'm sure there's more to the story, right?
Yeah.
What else makes them such a game changer?
Well, LEDs are incredibly durable.
Oh, okay.
They're solid-state devices, meaning they don't have fragile filaments or gas-filled tubes that can break easily. They can withstand vibrations and shocks much better than other lamp types, making them ideal for applications where robustness is key.
And they're tiny. They are tiny. That opens up so many design possibilities. I'm thinking sleek fixtures, hidden lighting, and creative applications we haven't even imagined yet. I remember reading about how LEDs have enabled the creation of those incredibly thin and flexible OLED panels that are used in some of the latest TVs and smartphones.
You're right, the small size of LEDs allows for incredible flexibility in lighting design. We're no longer limited by the bulky forms of traditional bulbs. LEDs can be integrated into almost anything: furniture, walls, ceilings, even fabrics. Remember that glowing wallpaper we mentioned earlier?
Oh, yeah.
That's made possible by OLED technology.
It's amazing to think about how far lighting technology's come.
It is.
But I'm curious about the technical side of things.
Sure.
We've talked about the efficiency, longevity, and versatility of LEDs. But is there anything else our listeners should know about how they work or what factors affect their performance?
There's one crucial aspect of LED technology that often gets overlooked:
What's that?
heat management. Even though LEDs are much more efficient than other lamp types, they still generate some heat, and if that heat isn't dissipated properly, it can damage the LED chip and shorten its lifespan.
So it's not just about generating light, it's also about managing the heat that comes along with it.
Exactly, and that's where heat sinks come in.
Heat sinks.
They're typically made of metal, like aluminum, and they act like heat magnets, drawing heat away from the LED chip and allowing it to dissipate into the surrounding air.
It sounds like heat sinks are the unsung heroes of the LED world.
They truly are essential. And speaking of unsung heroes,
Yeah.
there's another fascinating process involved in LED manufacturing that ensures that those beautiful, consistent colors we've come to expect. It's called binning.
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 I've never heard of that before. What's it all about?
When LEDs are manufactured, they don't all emit light with exactly the same color characteristics.
Okay.
There can be subtle variations in color temperature and other optical properties. So to ensure consistency, LEDs undergo a sorting process called binning. They're grouped together based on their color characteristics, ensuring that LEDs with similar properties are used together in a particular product.
So it's like a quality control measure to make sure that when you buy a set of LED bulbs or a strip of LED tape, you can be confident that they'll all emit a consistent color of light.
Precisely, binning plays a crucial role in creating those seamless lighting experiences we've come to expect from LEDs.
It's amazing how much attention to detail goes into something as seemingly simple as an LED light bulb.
It is.
It's clear that LEDs are the dominant force in lighting today, but is there anything on the horizon that could challenge their reign? Are there any emerging technologies that could disrupt the lighting landscape?
There are a couple of contenders, though. They're still in the early stages of development and haven't quite reached the mainstream yet.
Okay.
One of them is organic LEDs, or OLEDs, which you already mentioned earlier in the context of those flexible displays.
OLEDs.
OLEDs.
They're fascinating.
They are.
What makes them different from regular LEDs?
Unlike traditional LEDs, which are essentially tiny points of light, OLEDs can be made into thin, flexible sheets that emit light across their entire surface.
So imagine an entire wall or ceiling that glows with a soft, diffuse light. It's like erasing the boundaries between lighting and architecture.
You're catching on. OLEDs offer incredible potential for future lighting designs. They could be integrated into furniture, fabrics, even clothing.
Wow, we could be wearing our own personal light shows.
The future of lighting is definitely looking bright.
Speaking of bright futures, what's the other emerging lighting technology you mentioned?
It's called plasma lighting.
Plasma lighting, that sounds almost futuristic.
It does.
How does it work?
It involves using a high-frequency electric field to excite a gas similar to fluorescent lamps.
Oh,
But without the need for electrodes, this creates a plasma that emits a very bright and efficient light.
and what are the advantages of plasma lighting?
Well, it can produce a very high light output comparable to HID lamps, but with potentially better color rendering. And because it doesn't rely on electrodes, which can wear out over time, plasma lamps have the potential for very long lifespans.
So it's like combining the power of HIDs with the efficiency and longevity of LEDs.
In a way, yes, but plasma lighting is still in its early stages of development. There are challenges to overcome in terms of cost and practicality before it becomes a mainstream lighting solution.
It sounds like the world of lighting is constantly evolving.
It certainly is. From the humble incandescent bulb to the cutting-edge possibilities of OLEDs and plasma, lighting the quest for better, more efficient, and more creative ways to illuminate our world continues.
This has been a truly illuminating deep dive.
It has.
But before we wrap up this first part,
Yes.
let's take a moment to recap what we've learned so far. We started with the incandescent lamp, the granddaddy of electric light sources.
The OG.
Simple, yet inefficient. Then we explored halogen lamps, a brighter and longer-lasting iteration of the incandescent concept, thanks to that ingenious halogen cycle.
Right.
Next up were fluorescent lamps, a major leap forward in energy efficiency relying on the magic of fluorescence to convert UV light into visible light.
It's pretty amazing.
We even touched upon CFLs, those compact versions of fluorescent lamps that aimed to replace incandescent bulbs but weren't without their quirks.
Right, they had their challenges.
And let's not forget the heavy hitters, HIDs for powerful illumination in large spaces, and sodium vapor lamps, champions of efficiency, but not so great with color accuracy. And then we arrived at the stars of the show.
LEDs.
LEDs.
Efficient, long-lasting, durable, and incredibly versatile LEDs are revolutionizing the way we light our world. And with emerging technologies like OLEDs and plasma lighting on the horizon, the future of lighting is full of exciting possibilities.
Stay tuned for part 2 of this deep dive, where we'll delve deeper into the nuances of these lighting technologies, explore their impact on the built environment, and ponder the fascinating possibilities that lie ahead.
It's going to be great.
You won't want to miss it.